Okay, now first of all, we talk about what is an oscillation now. So oscillations are just defined as a repeated back and forth motion on either side of a fixed position now. So there are generally two types of oscillations we call it. One is free oscillation, one is called forced oscillation. So what is free oscillation? Free oscillation is when we give um, an oscillating system an initial disturbance only. That means we don't continuously oscillate using our hand or using a force. We just give it an initial disturbance, and after that, once we are done with it, then it will move by itself. Like for example, if you plug a guitar string, so you give it an initial disturbance. That plucking is an initial disturbance. After that, it will vibrate by itself. So as it's vibrating by itself, we call it a free oscillation. Or in the case of a forced oscillation, we must continuously give it a force. Example, if let's say I hold a ruler and I shake it in my hand, so the ruler starts to oscillate. But I continuously shake it in my hand, so that's called forced oscillation. Because it's not oscillating freely, I'm forcing it. Now, every time you give it a initial disturbance, it will undergo free oscillation, and it will always oscillate as a natural frequency one. This is for a fact. Because every oscillating system has a natural frequency. So what's a natural frequency? Is the frequency at which the oscillating system will oscillate when given an initial disturbance. For example, when you plug a guitar string, if you keep plucking the same string, you get hearing the same note, right? Because that is their natural frequency. Right now, so any oscillating system has a natural frequency one. If you pluck it or give it initial disturbance, it will oscillate natural frequency. But forced oscillation, because I'm the one providing the force, I can adjust whatever frequency I want. So it will oscillate at the forcing frequency, not at this natural frequency. Okay? Now, let's talk about free oscillation first before we talk about forced oscillation. Now, whenever you give an oscillating system an initial disturbance, it will oscillate. But can it oscillate forever? It will die off. Why does it die off? It's because energy is lost. And when energy is lost, we call it damped oscillation. So we call what's damped oscillation? Oscillation in which the amplitude and hence the energy decreases exponentially with time due to damping forces. So what is damping? Loss of energy in the oscillating system due to resistive forces such as friction or air resistance. Understand now? So how does your actual graph look like? That means if let's say I give it initial disturbance, imagine you look at the guitar string, it starts to die off. So how does the amplitude drop with respect to time? Now, if you observe how the oscillations behave, can you see it dropping with time? But this is an exponential drop. That means it's not dropping straight line. So what is the difference between a linear drop like this, a linear decrease, and an exponential decrease? A linear decrease means your amplitude drops the same amount. That means the energy loss is the same. But exponential drop means initially, can you see it drops a lot? Then it drops less, then it drops even less, it drops even less. Fair enough. So that means over time, when the amplitude gets smaller, the energy also lost, but less energy is being lost. So the rate of energy loss is getting smaller. So this is something you must know when you draw. Because when they ask you to draw the graph of damping, you have to draw this. So why? Why does it drop exponentially and not linearly? It's because whenever the amplitude is big, you lose more energy. Amplitude is small, you lose energy. Okay, why? One of the factors is easier to remember, easier to understand is air resistance. Now, if you are, let's say, considering an oscillation, and let's say we talk about sitting on a swing. Now, if you are swinging with a big amplitude and swinging with small amplitude, is the period of oscillation the same? Let's say I give you a big push, right? So you swing with very big amplitude, and I measure the period, right? Compared to I give you a very light push, and then you swing with very small amplitude, is the period the same? It's the same. Because even when you do the oscillation in the lab, do you realize that sometimes when you pull the pendulum, sometimes a bit further, sometimes a bit nearer, do you exactly measure what angle? But you don't care, what? Because the period is about the same. So how can it be the same? When you're moving with big amplitude and small amplitude, how can you have the same period? Because different distance travel, right? It can be the same, provided you are moving faster when you're moving with big amplitude. So when you're moving in big amplitude, you cover a bigger distance, so you just move faster. Then you cover the same oscillation, one oscillation in the same time as a small oscillation. A small oscillation travels shorter distance, so it doesn't have to move so fast. So which is why the speed is different when they're moving. So which one will have higher air resistance, when you're moving fast or moving slow?
Fast.
Yeah. So when the amplitude is big, you're moving faster, so the amplitude is big, right? So therefore you have more air resistance. So therefore you lose more energy. But when the amplitude is small, you're moving slower. So you have less energy lost due to air resistance. Does it make sense?
Yes.
Right. So it is actually exponential drop. Right. There are different degrees of damping. One is called light damping, one is called critical damping, one is called heavy damping. So what is light damping? So light damping, we can consider these three cases. We can consider as light damping because when we displace the oscillating system, can you see it overshoots before coming back?
Yeah.
So this one also overshoots, this one also overshoots before returning to the equilibrium. So you can generally call it light damping. But once you increase the damping even more, because this one is increasing damping along the way, when you increase to this called critical damping, then what will happen is the displaced mass will straight away return to the equilibrium and never overshoot. So it doesn't overshoot at all. Compared to all this overshooting, it doesn't overshoot. But what about heavy damping? If you increase the damping even more, then it will be heavy damping, where it will straight away also return to equilibrium without passing through it. But what's the difference between heavy and critical? Critical damping will return to its original position without passing through it, but in the shortest time possible, this very long time. So the shortest time you can achieve this is called critical damping. Because if you notice, all the light damping, the first time it passes the equilibrium is very short. But this one is a bit longer, but it never overshoots. So the shortest time you can achieve without overshooting is when you get critical damping. So this is the definition of critical damping. Damp oscillation in which the displaced mass returns to equilibrium position without passing through it in the shortest time possible. Alright, so another thing you need to know is examples of critical damping. So I'm going to give you now in the next slide. So one of the things they will ask you is to give examples where critical damping is used. Now critical damping is very useful. Some people think that such a big damping energy is lost is bad. But there are few examples where it's useful. The first one is in your car suspension system. Now a car suspension system consists of two parts. One is your spring. Inside you can see the spring?
Yeah.
And inside the spring is a damper. Alright, the Malaysians call it absorber, shock absorber, but this is actually a damper, we call it damper here. So how does this whole suspension system work, right? Now, the spring, why do you think we need the spring here? The spring is to actually cushion the impact. Because you see, if let's say the car had no spring, it's like a supermarket trolley. Whenever they make any small bump or any hole, the whole thing rattles and shakes. So that's how your car would be if there's no spring. But with the spring, it's sort of like cushions your impact because it lengthens your impact time when it's being compressed. So it cushions the impact. But if you only have the spring, what will happen is, if it, let's say, hits a bump, the tire hits a bump. So what will happen is, you start to oscillate because it bounces up and down. So your car whole thing will bounce up and down, which is dangerous and also quite dizzy anyway, right? But if you don't want it to bounce so much, that means after hitting the bump, the spring compress and straight away go back to normal. So we don't want it to bounce. That's why we need critical damping, because it gives you initial disturbance, return straight to the equilibrium position without passing through it. So how do we achieve it? Is by using these dampers. How does this damper work, right? Okay, example now. Now inside this damper, there's this piston that is moving up and down whenever it hits, whenever your spring is being compressed or extended. Because once it compresses, it will extend back again. So if you compress, the piston will move up. When they extended, the piston will move down. So the piston is actually moving inside a small hole. So they cut the cross section here. So you see this cross section here, but you need to imagine that this is circular and around it is a circular small gap. So it's a small gap for the piston to move in and out. So if you hit a bump and the tire moves up, then this piston will push up, right? So it's pushed up, it will displace the oil from the top and squeeze it through the small hole down here. So do you know that it's very hard to squeeze a very viscous liquid through a small hole? Like when you try to squeeze water out of a syringe, you notice there's a resistance to your motion. So imagine the hole is even smaller and you're squeezing something even more more viscous like oil, for example, right? So what will happen is it will actually require work to be squeezed out. So when you require work, where does the energy come from? From the KE of the tire pass on to the piston because it moves up. So it means the KE is used to do work to squeeze the oil from the top to the bottom, and that work done is lost as heat. But then don't forget the spring is fully compressed, so now you have to push back out because you displace it by compressing it. Now you got to come back to original. When it comes back to original, the piston has to come back out again. So the piston, when it comes out, will again displace the oil from the bottom to the top. So again you have to do work, so that energy is lost as heat again. So if you calibrate this, how big the hole is and all that, how long you move up and down and all that, then you can adjust until you get critical damping. Alright, but normally the cars we say theoretically is critical damping, but if you go and try it out in your car, right, how you try, you just go to any four corners of your car, for example, right, you just draw a car here, alright, so maybe I try to draw 3D. Alright, so this is a car tire, and then this is the windscreen, right, and then this is the roof, right, okay, something like this. So all you have to do is to actually push down on either one of these four corners. Okay, give it a quick push down, and then you see it will bounce up and down now. Okay, if there's no critical damping. If critical damping, the more you push up, you straight away stop. Go up and stop back in the equilibrium. But if you notice, most of the car absorbers don't really they're not exactly critical, slightly less than critical. So you go up, you push down, you go up slightly, and then you stop. You go overshoot slightly and stop. So overshoot slightly and stop. So you can test four corners. But then don't go throw away your damper or absorber. Say, oh, because it's no longer critically damped. But that's normal. Okay? Alright. Now another example of critical damping where you can use is in the laboratory meter, such as your ammeter or your voltmeter. We call it the analog meters, the one that uses a needle. Now that one also has critical damping because you notice that when you connect the electrical supply, the needle deflects. When you disconnect, it comes back. That means there's a spring that brings it back. So actually how the spring works, it opens up now and then it closes. So when it opens up, it actually deflects. But then the thing is, whenever you deflect, right, if there's just a spring, then the needle by right, I'll show you. If let's say this is your meter, if let's say this is the needle, right, so let's say it deflects, right, so by right it will oscillate a bit. When you reach the end, it goes to here and it oscillates a bit because of the spring one. But you notice if you see carefully, it does move a little bit one. But it seems that it stops right now because it's critically damped. But most of it I told you is not exactly critically damped, it's slightly less than critical damped. So you see it moving if you see nearer. So how does this critical damping work? We will explain later in EM induction. But you just have to state critical damping can be used in these moving coil meters. Alright?